here we are. Hello and welcome to what could be the last of these Erica Synth build-alongs. Well, not quite the last, because we're going to do another one when we solder it together, but the last breadboarding of a module from our very nearly complete Erica Synths modular. Oh, it's a bit dusty in places. It's nice, it's been quite a journey. We've been doing this since January, which is extraordinary. Once a month, more or less, because here we are in month 10, and this is live stream number 10, project number 10, although there are 9. That's where we are. So today we're going to fill up this little tiny space here. Not quite today, we will on the next one, but we're going to look at the thing that fits into this space, if you're with me, and that is the Wavefolder. Now, having a bit of a scan through the manual, I noticed that there's a few nice tasty breadboardy kind of things. So just pausing because somebody says they're buffering. Video is buffering. Let me just let me just check with the house. One second. Probably. Let me just have a poke over here. No sound at your end. I'm going to pop the video back on just for the moment, okay? Which is what? That one. Which is... Hang on. Oh dear. Which is that one? Okay. We're going to give it another go. I'm sorry about that. I am really sorry. It drives me nuts. But hey, let's give it another go. So, please do excuse the first 10 minutes. I hope it is looking a bit better as far as I can see. So let's go with that, shall we? Let's just press on forward. So, excuse me, you're very welcome. This evening we are going to build the Erica Synths Wavefolder out on a breadboard, following the instructions that are available on the Erica Synths website. Through the shop for the Wavefolder, the EDU DIY, and we're going to follow them through in order to try to grasp what the Wavefolder circuit is all about and then build it out potentially on our breadboard here. You can build along with me if you wish, or just watch, or just get in the chat and chat to the other lovely people who are there talking probably about other things as I do my thing over here. So that's nice. But it's good to see you. Good to see Ian. Ken, seen you already. Aquatic Borrelius, that's a good name. I like that. And I have tried a Moog Matriarch. I tried one at Super Booth when it first came out, and the one I tried was broken, and it was not very impressive. But I understand it to be an awesome thing. I would love to have one. Other than that, I hope this is not buffering too badly for you now, and that you can hear and see what's going on. So let's get ourselves to it. So I have already measured. I've already measured the resistors. So we are ahead of the game in that regard, even though we've lost 10 minutes just with shenanigans. So let's have a look here at our manual. Like I say, you can follow along. So it even says, let me see if I can just get us looking at the right thing. I'm just going to need to, just give me a second. Which one is that? That's that one. I want to have number 5. 5 is what I need. Let me switch to number 4. 5 should be the manual for the most part. So this is the Wavefolder. Wavefolding is more of a West Coast concept, so we say. Now, I would highly recommend going and watch Mark Doty's Automatic Gainsays series of videos on the whole East Coast West Coast thing, because apparently it's a whole load of baloney, which is good to know. But I don't think there's any doubt that wavefolding was something that came out of booklet synthesis over on the west coast of America. Or it probably existed somewhere else, who knows? But this is the concept of folding a simple waveform upon itself in order to generate more harmonics and more complex tones. That sounds like a good thing to have in our rack. So, to start off with, we have just a random circuit with no explanation whatsoever. Oh, I know who that is. Moritz Klein, who wrote this manual and these materials, he says that he came up with a super simple BJT based double wavefolder. Now, somebody asked previously what a BJT based wavefolder is. I have no clue, but it's just something that was in the marketing copy for this particular module, so I wrote that in my article about it. No coast is the future. But what we appear to have is we've got like resistors. We've got a resistor that folds back on itself over here, which is nice to see. We've got some op amps, some transistors, op amps, transistors, op amps, resistors. Easy. This looks like an easy one. Does there appear to be 2 sections for a double wavefolder? There does, I think. To some degree. Anyway. So it says we'll need a suitable signal to fold, which traditionally has either been a sine wave or a triangle wave. And since the VCO produces none of those, does it not? Oh, it's got a sawtooth or a pulse wave. Look at that. Added complication. That's interesting. So the VCO that we have in our system doesn't produce the waveform we need to fold. So we're going to have something in here which does that. And you will find that within the front panel of our what's it here, there is a saw to triangle inverter converter button thing. Input. So that's what that's about. So here he designed a super efficient little sawtooth to triangle converter that uses the same basic working principle as the main wave folding circuit. Interesting. How interesting. So bill of materials, bunch of resistors. I've been through those. I think I have them all. Bunch of capacitors. We've got both. Let me go on to this one. There we go. Bunch of capacitors. You can see those resistors. Sorry. You've got a couple of electrolytic capacitors here. 47 times 2. Those are 47s. Stick those out of the way. Then you got some of the big square one. Making perfect sense. A bunch of the little squitty ones. 4 of the 104s. And then some 2.2s. Oh. Right. I've only got one of those. That must be, where are my glasses? Hang on. I don't know. Where I saw them. Where did they go? What did I do with those? This is going to be a bit of a problem. I can't find me magnifiers. I had them hanging up over here. There they are. They're up on the wall. Hang on. Spiders, get out of it. So, let's have a look and see what I've got here. So that's 104, or 104 ceramic. There should be 4 of those. I've got 1, unless these are also 104s. Yes, they are. So, okay, so I've got 4, which are just slightly different to each other. I've got those 2. I've got the foil one. Got another foil one here. That's the 2.2, of which I have just the 1. That's the 6.3. Right. So there was one which was... No, that was that one. Alright, so there's a possibility that I'm down 1 capacitor. I seem to have 1 of those. But it may yet turn up, or we may not yet need it. Sometimes there's some adjustments that are required. So let's not get overly concerned. Should have some diodes. Yeah, they're always usually to do with the power. Which are those 2 fellas there. A couple of transistors. There should be 4 of one type, which are these ones. 5. I don't know. I don't quite know what that says on there. 5, 4. 5, 4 something. Yeah, 5, 4, 8. Okay, got it. And there's 2 of the 5, 5, 8s, which must be these ones here. Yes, they are. So that's good. We've got some regular pots. A regular pot. A trimmer. That's this blue thing here. A couple of jacks. And a TL074 op amp. Bunch of op amps. Quad op amp. There we go. Cool. Great. So we'll come back to powering in a minute. So let's have a look at our wave folding basics. Okay. So we need to make sure we understand what wave folding actually is. Okay, here we go, boys and girls. It's a term that's hard to misinterpret. Good, because it basically folds a waveform. You've got a folding threshold, and that bends that over there. It's great. Always looks good on an oscilloscope. It's awesome. Now it says it gives, oh hang on, in practice this would create a bunch of additional overtones which result in a metallic feel. It's not suitable for everything, so for the wave on a square wave, wave folding doesn't actually achieve anything. And also for sawtooths, it doesn't really achieve very much, although it does depend on who's doing the wavefolding, because I've seen some good wavefolding over sawtooth waves before. For instance, on the Pony oscillator from Bafako. That does sawtooth wavefolding, triangle wave, which I don't think is what happened on the Pony. But hey, so the simplest of wavefolders, how do we make it happen? Well, this circuit will probably be quite complex. Well, it's not. Apparently, all you need is 3 components. Some resistors, an NPN transistor, and if you set them up like that and send an oscillation into the transistor's base, we can pick up a folded version at the collector. So, let me get my mouse involved so you can see what I'm looking at. So our input comes in here, so waveform goes into there. And because of these, I mean, you've got 2 identical resistors going one way or the other. Plus and minus 12 volts. Somehow for an output, it folds it. I don't even know how it gets through. I mean, how does it get through? Because surely at the base of a transistor, it doesn't actually go through. The base of the transistor is about turning that on so things go from that way to that way. So what must be happening? I guess you're transferring whatever's coming in to... I don't know. This is the thing. I don't know. Well, I'm here to try to learn. So if you've worked with transistors before, well, of course we have, but... Oh, hang on. Oh, what you might say, apparently, is that this is just a bog standard amplifier. I'd recognise an amplifier anywhere. It doesn't really amplify anything. It has a gain of -1, so all it does is invert the input signal while keeping the volume the same. That sounds okay. So why do we call this a wavefolder? Because if you abuse it... I see. To understand why, let's dissect the circuit step by step, and we can split it into 2 sections. The resistor at the top, and the transistor, and the resistor below. Start with the lower section. So these 2 components in conjunction serve one simple purpose. They're meant to convert voltage into current. More precisely, the voltage we apply to the base into a current flowing through transistor and resistor. More precisely, the voltage we apply to the base into a current flowing through transistor and resistor. It still doesn't go in my head. Okay, but what is the relationship between those 2 variables? Yeah, there will be op amps. How is it that I'm being tripped up by the first simplest explanation? So the transistor on its own, the relationship between the base voltage and the collector current is exponential. See, this is voltage and current shenanigans again, and that's always going to blow my mind. Because if you put something to the base and essentially open the transistor, then current will flow. I understand that, I think. Conversely, for the resistor, relationship between the voltage across it and the current flowing is strictly linear. Okay. So you're talking in general terms, right? Something going through a transistor is exponential. Okay. Whereas going through a resistor is linear. Okay, I get those 2 things. Okay, next page. So when the components are paired up, okay, so you see the behaviors are clashing. While the transistor wants to ramp up the current, the resistor only allows for a linear increase. This means the resistor is the bottleneck in our system. It throttles the transistor. So for a given base voltage, the current flowing through the transistor and the resistor will be almost the same as the current flowing through just the resistor. Yeah, okay, because the resistor is restricting it. Okay. It says almost because the transistor uses up some stuff. Fine. That resistor serves as the exact hang on. Now let's look at the upper part of our amplifier wavefolder, which is just a single resistor connected to the positive rail. This resistor serves the exact opposite. It converts the current into voltage. Oh, my mind! The more current we pull through the resistor, the more voltage below it will drop. If we put this together with the lower half now, it should become clear why the voltage at the collector almost mirrors the voltage at the base. Because for every volt added to the base, we push an additional 50 microamps through the bottom resistor. See, like I say, we've been doing this for 10 months. Bingo, says Mr. Weekly. 10 months. I've learnt nothing. I don't remember any of this. Oh dear. It's like I come at this with a completely smooth brain every time. Every time. No, there's not a single notch has been made in my brain about any of this. I still don't understand this voltage-current relationship. Not really. I don't understand it so that when I look at it, I just go, oh yeah. I look at it and I go, what? I don't, what? Well, I mean, you've just told me that it's voltage, a changing voltage goes through a resistor in a linear fashion. Or a changing voltage causes a linear current change. Anyway, so which in turn means we have to pull that current through the top resistor. Because that resistor is of the same value as the bottom one, the voltage will drop by exactly 1 volt. Got that, kids? Good. Good. There are 2 caveats though. First, the absolute collector voltage will be a small but fixed amount higher than the base voltage. There's just some being used up. I get that. You can try this circuit out in the simulator. Let's do that. Let's most certainly do that. Right, so this is our amplifier inverter. So it inverts with a small change. Oh, Ohm's law, yeah. V over I. Resistance equals voltage divided by current, which means the current is a voltage divided by the resistance, which is linear. Is that what you're saying, Ken? Voltage is a force. Oh, God. So what I think this evening is going to be is just to watch me be in pain as I slowly try to wrap my head around this most simple basic electronics concepts. I've got an O-level in electronics, you know. I have. I mean, that was 40 years ago. I mean, I'm just looking at what I'm looking at. Are you looking at the same? Yeah. I'm just looking at a thing which is operating as a thing. I mean, it doesn't make any difference to me. Oh, look, I can pull that off there. I didn't mean to do that. So, presumably, I mean, I can... Careful now. I can speed it up. Does that make any difference? Not really. So... Okay, so let's not waste our time looking at something that's not going to do me any good. So, but what we have to come to understand is that more or less what's going in is being inverted. That's what's happening. Nothing else really. Is that really important? So the transistor eats up a bit of current while it's active, so they're not exactly the same. And this mechanism only works as long as the transistor can pull enough current into its collector. Okay. So let's look at the circuit's behavior with a graph. Let's do that. So we imagine we steadily increase the base voltage from -12 all the way up to +12, right? Okay. In the region between -12 and 450 millivolts, what the heck has millivolts got to do with anything? Oh yeah, sorry, yeah, okay, here. In the region between -12 and around 450, everything works as expected. The collector voltage drops in sync. The collector voltage, VC. So this is the base voltage. That's the collector voltage. So that's the stuff coming in to the top. So the base voltage being applied at the side. So the base voltage coming in at the top. They're going to stay the same to start with. But after the base and collector voltages meet, something strange happens. The collector voltage starts rising again. What's up with that? What's up with that? Thanks, Adamski. Okay, interesting stuff in the comments. You should definitely keep up with that if you're watching after the event. So, what was I saying? Oh yeah, what's up with that? So we've run into a phenomenon called transistor saturation. This happens when we try to pull more current into the collector than is available. Think of it like this. Okay, let's try to think. Think. If we'd remove the transistor from our circuit, we'd see 600 nanoamps, microamps flow through both resistors. We can't increase that current without bumping the voltage or reducing the resistance, because I equals V over R. So if we reduce the resistance and the voltage stays the same, the current increases. Or if we increase the voltage and keep the resistance the same, the current increases. That much, that we know. This we know. So, as we push the base voltage above 450 millivolts, the transistor tries to blow past that current limit. But since it can't get more current out of the top, it'll switch to an alternative strategy. Very interesting. I like the interplay, and I like these random numbers like 600. I mean, I guess they're using 12 and 20, aren't they? That's what they're using. That's why it gets 1200. That's why it gets the 600. Where the 450 comes from, I'm not so sure. But we're just going to take that as read at the moment. So, that strategy is putting large amounts of current into the base, which will not only cover the missing amount, but also increasingly substitute the current flowing into the collector. As a result, less current is pulled through the top resistor, and the voltage below it starts to rise. More precisely, for every volt added to the base, the collector will rise by the same amount. So in order to pull more current, it's having to increase the voltage. I mean, I'm assuming at this point that the transistor has like a dial that it turns in order to make that happen. Is that what happens? Does a transistor possess its own form of circuitry and control manipulation? So this means that we have two distinct regions in our graph above. One where the collector voltage is roughly the inverse of the base voltage, and one where it's roughly the same. Two distinct regions. So if we send an oscillation into the transistor's base, every part of the wave that crosses the 450 millivolt threshold will be folded over in the output. Reference 7. Let's set it up on a breadboard. Let's do that. Let's definitely do that. Right, okay, so for breadboarding and that, I've got to look at what on earth I'm doing. So let's just pop back up to the powering the thing, because I always need to remind myself of how to do this. So I'm going to have this way round. I can use that because that's already there. Just pull out these other bits. Now my breadboard is labelled differently to Moritz's breadboard in the manual, and so I've developed a way of trying not to make myself go crazy by having mine slightly upside down to his. It will become clear, kinda. But here are my 9-volt batteries, which have lasted this entire thing rather impressively. I think you'll find rather impressively. So let's plug that in there, plug that in there. So for this, so my plus and minus is the opposite to his plus and minus. I'm not letting that worry me. Because what's more important from my point of view is that these numbers here match up to the numbers on the manual. So I am personally ignoring the plus minus here, and just wiring it up correctly. Now, in order to do that, I need positive from one battery into the inside track, and then the other one, which is negative, or ground rather, is going to be connected to ground, no, positive on the other one. Let's get this right, which is there, and then finally the negative goes on the outside. So for as far as power goes, I've got one battery negative on this outside, I've then got positive on the inside, negative on the inside connected by this cable here, and then positive on the inside at the top, and that should give me sort of +9 ground, +9 ground both sides. Oh, I don't know, it'll make more sense in a minute. Cool, okay, you keep talking, that's fine. Right, let's go back to our first bit of breadboard. This is going to be awesome. Yeah, so we now got ground at the top, positive, ground at the top and the bottom, and negative. That's how this is laid out. Is that all right? Are you getting all that? Good, good. Right, so they're doing something all the way over here. So we're going to start off with a thingy. This is going to be over 25, 1, 2. Like that. And there's a space, one more. So I just need to angle this a little bit better. Oh no, I've forgotten which way round I'm going. This needs to go. Needs to go a bit like that. Let's zoom that in a little bit. Got it? Good. Right. Get the battery out of the way. So just need a boring old piece of wire to go from the edge of that to ground, obviously. I haven't done this for a while. I've lost any sense of how am I doing this. How do I do this? So I need that to go to like so. Oh, that was just complete nonsense. Right, where's my thing? Where's my box of bits? Let's do this again. Come on, man. Come on. Come on, then. You can do this. More fingers and thumbs. Right, that in there. Come on. Come on. That's it. Oh, dear Lord. Everything is connected in strips, if you see. So this is now taking the ground of the jack plug to ground. Okay, I won't explain this for too long. I'll just do it every now and again just so people know that they're with me. Now I need a 20k resistor, which is one of these. 20k. I measured these earlier. And I need an N transistor. Which one is those? I've got two transistors. I've got the 558A and the 548. If anyone can tell me which one to use, that would be great, while I just put this resistor in. So this is going in on 35, I think. Yeah. And it's going across to the negative. 35 across to the negative. So this is the bottom side of it. I need another 20k. Geez, really? The lonely ladies. I know. I know. Well, somebody said I was fragrant. I mean, Nick was talking about aftershave in one of the weirder moments of the Sonic State stream. So, not 35, so it's going up a couple to the end of that one. That's going up to positive. Onto there. So 558 is PNP, not NPN. Okay, so what are you saying? Which one are you saying exactly? So if I go scroll back up to the bill of materials. So the 548 is NPN. Is that what I want? Go back to where this is. We're talking about a transistor. When did he mention the transistor? NPN transistor. So we're going to use the 548s then, yeah? Flip the breadboard, blue is the ground. What are you talking about? What are you talking about, Dennis? 548. That's these ones. Because on the ground is the red one on this one and blue one on this one. No, it's not. Ground is, hang on, no, yeah, ground is the top one on both strips. If you look at the two strips, forget the colours. Colours are irrelevant. Two strips, top is ground. And then the bottom is positive. It's attached to the positive there. The bottom one here is negative, attached to negative. Got it? My breadboard is labelled differently to the one in the manual, so they're never going to be the same. Got it? You good? Yeah. Adamski, the ones you're talking about are neither of these. So let's get this in, otherwise you're never going to get anywhere. Try and put it the right way around. This one leg seems to go onto the end of the 20 here. So it's going to go in like that, that way round. I've then got I've got to jump over the thing because one end of it is going to the 20k going at one side and one end of it is doing 20k going the other. So I'm jumping the void. So I've got one leg going to this 20k to positive and I got this other leg going down here to negative, which is what it was all about. Then we just need the base connected to our jack input. That's what we're going for now. Very exciting. And that's going for the center one to that leg. Which I think is going to look a bit like that. Good. Right. How are we going to see or hear or experience what that's actually achieving is my next question. So, well, if I send it a what's it, so let me plug in a triangle sine or sawtooth wave in the jack socket connected and monitor it with an oscilloscope. All right, this is going to be interesting. So I've just got the power for the Erica Synths bit thing over here. Where's the input? There's the input. Right, so I've got that plugged in. I then got a ridiculously long cable. I don't know if I need that, do I? Can I have a less ridiculously long cable, please? Anyone? Oh, look, there we go. Oh, but that's a bit... Oh, right, so sawtooth out. Plug that in there. Now what the heck do I do? See, that's going to be too heavy. I need a more pathetic cable. That's a more pathetic cable. Okay. So I then have, when I've got me what's it here, do you think I can use this as some method of detecting something? I mean, you've got to think that it might be possible. So I've sent it a thing while monitoring the voltage at the collector with an oscilloscope. You recommend to route the input through a mixer. Well, I can do that because we have a mixer on our thing here, don't we? So mixer in, out. So with this, this is ground, so we stick that into somewhere on the ground bit. And this we want to measure the emitter. Which one is the emitter? No, at the collector. Don't know. The output is at the blue cable. Well, I mean, if I plug it in anywhere, nothing bad's going to happen because we're not exactly talking about big anythings. So, I mean, we've got a transistor, right? What are you looking at over there? You're looking at this, the same thing. So, let me see if I can get this a little bit more in play. Come on, reason it out, boy. Reason it out. You can do this. Because you know that the emitter over here is going to what? Come on, the emitter is going to minus, going to the negative. So the one with the arrow on, that's the emitter, yeah. That's going to negative. So I want the one that's going to positive. Yeah, does that make sense? So as far as this is concerned, positive is up this side. So as the man said, the blue cable. So I need to stick this in here. What was I hoping to achieve? What was I hoping to see? I was hoping to see something, wasn't I? I think so. But I've got diddly squat. That's coming. Oh, I got it completely backwards. No, I haven't. That's going into there. That's the input. Input 1. Input levels all the way up. That's the output. That output is going into my thing here. Is that connected? That should be connected to the back. That's connected to the front. That's connected to one bit. That's connected to there. That's connected to the middle. That's connected to there to go out. Now it could be, oh look, that's not even on the metal. Let's try it on the metal. Oh look, something's moving. Wait for it. Wait for it. Let's adjust some random switches on me thing. Okay, DC is what I want. Oh, 5 volts could be alright. What's this change? No one can remember. My goodness. Let me turn that down, see what happens. Flat, and then something going on. Now, what I need to do, flat, something going on, I need to change. How do I do this? Think, boy, think. Okay, I've got 10 milliseconds, let's go back to that. Okay, are you seeing that? I've got a bloody flipping Nora. Got a Nora cable in the way. There we go, put that in. Oh, I had something there and then I blew it. This is just out of reach. There we go. Look at that! Flipping heck! See, that's a sawtooth going in there. That's then folding. Are you seeing this? So can I change that to be bigger? I can. Look at that. So what it should be is a sawtooth. So what we're getting is a kind of a triangle, which would indicate that it is perhaps folding over. Perhaps. I mean, if I was to take the output of this, just as a comparison, plug that in there. Yeah, look, see, as a comparison, you see that? That is what is coming in, is a nice fat sawtooth. And then, because of whatever shenanigans is going on here, this is the result. It becomes a kind of a triangle. Yes. AC, what? Anyway, no, don't distract me with such complicated terms. Okay, good. So we can play with the volume and see what happens. Yeah, all right. So I guess at some point, is it going to go? If I go low enough, it should be just a sawtooth, and then as I keep pushing it, rather than getting a bigger waveform, it starts to fold. It does do that. See, I think my job here is done. I think we have successfully cracked the code to wavefolding. That mental frisbee. It looks like the 6EQU J5. Awesome. Well, I'm glad it does. That's great. Good. Right, next. Saw to triangle basics. So if you use a sawtooth wave, you probably noticed at a maximum volume it almost folds into a triangle. Yeah, we did notice that. Since wavefolding generally sounds really good, let me just swap you back to my manual. When applied to triangle waves, it makes sense to take a short detour and talk about turning our circuit into a proper sawtooth to triangle converter. To do that, the ideal way would have a roughly 450 millivolt offset to the sawtooth to centre it around the folding threshold. Okay, which would give us a symmetrical clean triangle. Isn't enough space on the module's PCB to pull this off, as it requires yet another op amp. Excuse me. So we have to find an alternative approach. The alternative approach with the smallest footprint is changing the relation between the collector and the emitter resistors. Awesome. Let's just get on with it. The relation between is more or less 1:1. So now let's drop the emitter resistance to 10k, shifting the resistance relation of 1:2. So you're changing one of the resistors, yeah? And that then changes the graph and moves the folding threshold. Interesting. Interesting. So apparently it doesn't result in voltage relation across the board. Instead we get a 1 to -2 relation in a non-saturated region. Oh, good. While the saturated region sticks with the 1:1. But that's not all. As you can see in the graph, the folding threshold also noticeably drops. This is really interesting. Because instead of adding an offset to our input sawtooth, we can simply lower the folding threshold to make them both line up. Great! An unintended side effect: if the voltage relations in the saturated and non-saturated regions differ, then our output triangle will be asymmetrical, since one side is going to be more slanted than the other. Not ideal, but since we care about the small footprint here rather than getting a perfect triangle, it's a concession we can reasonably make. Oh, I don't like all this compromising. You know, how can you trust anyone who's just going to give away everything at the moment's notice? Anyway, there's a problem with this approach though. Oh, is there? Every transistor is different. Well, why don't they make them the same? When it comes to a natural folding threshold, i.e. one of them where we're getting equal resistor values. The 450 millivolts we've been assuming so far are just a rough average. See, I did ask where that number came from. It's just made up. This means that the added resistance working for your specific transistor will not work for most others, so we'll have to go with an adjustable solution instead and use a precision trimmer, alright, to set up as a variable resistor. Great. Great, okay, so this has all been moved now. What are they trying to do to me? So let's have a go at this. So this is what we're doing again. We are trying to create a better triangle. Right, so let's pull this out of here. Take those two things off. So we need to take this fella out of there and this. So we're just leaving our little setup. This plug is going way over, but I've got other things in the way over there. You can't just go steaming all the way out. Good Lord. How am I gonna? I can't. All right, I'll have to make it up. So it goes over on 5, on 4, like that. I'll have to just do a bendy cable. That'll be all right. No one's going to mind. Who's going to know? Ah dear, it's so funny. Oh, let's use one of these orangey ones, I think. So I need to go to ground with this end here. So stick that in there. That's just going to go at a bit of an angle. Who's calling me? Oh no, apparently it's just the weather. Right, that goes in there. So I've got a 10K and I've got the trimmer, which is this fella here. So this needs to go in. It goes in at 14. 2 in, 14. Space for a couple, like that. I need another N going this way around alongside this space there. Right, I've got something needs to go from the middle to positive. Middle to positive. I need a longer one to go from the back end of this all the way to the middle base of the transistor. So back end, is that going to quite fit? Not really. That's a bit better. Back end to the middle. Good, good, good. 10K, 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 10K. Here's one. Gonna need 2 of these by the looks of things. So 10K is going to go from. Where is that going? That's not connected to anything. Oh yes, it is. It's connected to the adjustable, to the variable, to the pot. The what's it? So this is going all the way across to this that leg and to that leg on the trimmer. See, if I put it further to the right, Steve, I'll then start losing track. When this gets more complicated, the numbers are very useful in how you're laying it out. Just if you're remarking about that, there's always a reason why I do what I do, because I mean, although it doesn't seem like it, I have an immensely large brain and it's doing all sorts of different things at the same time, and one of those things is making sure the whole thing hangs together ultimately. So there tends to be reasons why I'm doing what I'm doing, even though it looks like floundering. So this is going all the way down to negative, isn't it? On that third leg to negative. And I need to hop over. Those brown ones were good. Yeah. Yeah, see, I haven't done that quite right. This blue one here should be 1 up. Just getting a little bit tight. There you go. And this one can jump the fence. Oh, go on, just go in the hole. Go on. Oh, good. Good, good, good. So how are we doing? I think that's the lot. This is not really involved, this bit over here at the minute. So I've now got a little thing, a trimmer going in. So I'm going to need to find a little screwdriver. I should think. That fits. Right. So what happens now? After you've set this up, send the sawtooth wave into the jack socket, sawtooth wave. That's this one. I'll put this one into the socket. While monitoring the voltage, and then play with the trimmer. So we've got to do this thing again. And to ground, that goes into ground. And this has to go, I guess, between the trimmer and the positive. So in there. It's not giving me much at all on my thing. Did I break it? Don't know. Still appears to be on. If I turn the trimmer, what happens? Something is not quite right. Yeah, right, something's got quite right. That's plugged in. Take that out. So it's definitely got a thing going on. So let me check that. There's nothing going into pin 3 of that, is there? That 10K is going to pin 1. Oh, have I? Yes, I have. No, I have crossed that. I've crossed that down to there. That's going to that one. That's going to the middle, going to that first thing. This over here is going to ground, which it is. But nothing going into pin 3. I mean, it may be that that's even upside down. That's middle pin. Middle pin going to positive. The resistor is going to the far leg. When I plug that in there, I get absolutely nothing on the screen. It's odd, isn't it? Put it there. Alright, let's put it there. Alright, if I just put it after the, just before the collector. Maybe I'm just putting it in the wrong place. I don't really know. Okay. Other people are agreeing. So that's looking like a pretty nice triangle. So what happens when I turn this screw? Is that better or worse? That looks slightly worse. Let's go the other way. Yeah, nice. Is that what I was trying to achieve? Do you get the gap between the rising and falling slopes disappear? Yeah, that's what I got. Look at that. Great. So you got a good looking triangle. Yeah, great. Next try. Increasing and decreasing the input signal's frequency. You'll notice that your triangle suddenly doesn't look so good anymore. Oh no, what a shame. So over here I've got the frequency. Oh no, mine looks alright. Why, what's the matter with yours? I mean, it's a little bit up and down. but that's waveforms for you, isn't it? Eh? Eh? Because a slight shift in a short sawtooth vertical offset across the full frequency range. Typical byproduct of AC coupling. Not much we can do to prevent this, and so instead we rely on a simple but effective fix. A low pass filter. Great. So low pass filter will cause the gap to be smoothed, resulting in a less noticeable buzz. And then we want to boost and buffer the signal to avoid loading effects. Okay. Finally, we should try to increase the converter's input impedance a bit. So lots of extra bits just to smooth this out. Want to put trimmers on both sides? Don't know. So, and here's the whole thing, what it's put together. So this is what we're going to do next. So essentially we're putting in a buffer, we're putting in a low pass filter to just sort of make it all work a little bit nicer, and that requires the addition of some op amps, which is always probably the most exciting bit, because we all love op amps. We've learned to love the op amp. So we've got a bit more breadboarding to do. Let's do that. Note that the buffer transistor will add a bit of negative offset. Yeah, I don't really care. So once you've set this up, you have to fiddle the trim again to get the best results. Well, of course, naturally. Make sure you've set it up exactly as shown here, because you could blow the bugger up. Yeah. I know. Right, so we are looking at this thing here. We're going to achieve that in some fashion on here. What time is it? It's 9:15. Good. I think there's still plenty more to do, plenty more to get interested in. Let's bring this up. Let's see if we can get this sorted. So let's just unplug the power for the minute, just until I've got my chip in. Right, so let's go from over here, because things have changed. We've now got another one of those transistors going in. And other bits of nonsense. So that's 5. That's over. Is that in the same place? That's up now at 12. That's kind of where it already was. Okay, so that's staying. This is no longer going there. I need to squeeze in another transistor. Op amps, yeah, Ken, for the buffer, yeah, totally all over that. So this is going to squeeze in here somehow. 1, 2, 3. Good. This long one now needs to be that other sized one, doesn't it? See, these are actually perfect once you get the hang of where the right ones are. So this is going from that leg to middle to and that leg. Then I need some more of those brown ones from that leg going to positive. Like so. I need a little one, not quite that small. go from middle leg to jack socket. Middle leg to jack socket. That leg to out. This leg going to the middle of this one. Got my 10k going from there to that one leg still. That middle leg going to positive. That's good. That one leg still jumping the shark, going down over here. Good. Right. So now I've got some new shenanigans. I've got the line next to it going over to ground. I need a 2N2. Wonder what that is then. 2N2. It's going to be a capacitor, yeah? That's the 2N2 capacitor. If this is where they ask for two of them, we are screwed because I only have the one. Unless I've lost one somewhere. Okay, so this 2N2 goes from there alongside to there. I need a 1K, 10K, 1K. This is a 1K. Keep thinking. That goes from that one leg, that far leg. Does that goes there? 1K goes the other side of the 2N2. I need a 1 nano. What does that look like? Does it mean it one of these? Is it one of the 104s? Questions. So what page are we on? 17. Let's go back up to the bill of materials. 1 micro is the foil one. Okay. Back to 17. So that's the big chunky square one. Goes on the end of the 2N2 like that. And we have another 1K next to it. And at this point, I need to stick in our chip. Right, so get this round the right way. Got the nodule out the top. At the front end, this thing here. So this is lining up on line 26 with that 1K. That's line 26. Like that. Good. Now I've got a single piece of wire. That's too small, I think. I'm going to go for an orange one. That goes to pin 3 and the end of that one. Yeah, that's good. Pin 3. Ah, bendy wires. Do you remember when I was doing this with the big long wires? Back in the bad old days when I said, I'll just do it with what I've got. I was very obstinate. Or maybe the word's pig-headed. I'm not sure. But these little wires are a better way of doing it. Definitely. But they are fiddly in of themselves. So, you know, I'm not saying that they're perfect by any means. 100Ks, here we go. A couple of these. Ian, what you need is a grids. That's what you need. Funny enough, I've just purchased one. A microgrids. A kit I'm going to build. Because I've so enjoyed using the Eurorack. But I've now decided that I just need that little bit more. And the Eurorack is essentially a grids in a different form. It's based on the grids. It does a brilliant job, but I just want to do the full thing. And that essentially is a little drummer. It's a drummer you've got a little bit of control over, otherwise it just plays itself. Which is flipping awesome. Now I know a lot of people already do that. So I'm not going to be particularly different to anybody, but that's okay because drums don't tend to be that different. We all know the vibes we like. That's what I'm looking for. So good. So that's going up to a positive. We're completing an op-amp type thing. There's another 100K squeezed in there. Yeah, there you go. Day, is it? Could be. Yeah. I mean, the other day I just watched this YouTube video. This guy, I retweeted it. I took it on Twitter. Joe Hoskins, was it? Can't remember. Anyway, and he had a very small system, and he had a PAMS and he had a grids and a row of those procs drums, and it was just lovely. I thought that's exactly what I'm trying to do, and I'm farting around trying to get that to work, programming in drum lines, and it's all there, and with a great bit of control over sort of filling it and tripping it over and ratcheting and bits and pieces. Just brilliant, simple, easy. That's what I want. I don't want to have to mess around all the time, and that's what the Eurorack and the Consequencer thing has kind of shown me. But I need to go the whole hog. But I can't find any ones for real. I'm going to have to make one myself. So that's also, well, I mean, I do like making kits. It's just I've got a lot of things I could be building. A lot of things. Last thing I need to do is buy myself a new kit for something. Anyway, blah blah blah, blah blah. Lots of good stuff to come. I need like a 14-day week, and then it would be flipping awesome. You would not believe the stuff I'd be coming out with. But as it is, here I am on a breadboard, building out a wavefolder for you good people. Oh, I must be mad. No, it's good. I like it. I like it. It's good to commit to things, because if I don't commit to things, I don't get anywhere. I'm not going as far as PAMS. I probably will, but I'm trying to resist it. I don't want to have to learn a complicated clock module. I don't want to learn it. Dear oh dear. Anyway, blah blah blah. So I got this. That's still there. That's doing its thing. It's still not connected to anything. Over here, I did that line. I did that. I did a thing over there. I've got a 1K, 100K. I've got a line over there. That line there, that's still crossing the streams. I've got a 1K going with that and with that. Got 1k in there, those 100k's, that line, those two lines, and that line. So that should be it. And after all of this, I think what I understand is that I'm going to get a slightly better triangle. So that's awesome then, slightly better triangle. Let's see what we get. Let's power that up. Let's get our thing in on the game. Oh, just behave. Thank you. Jam that in to ground. Put this in. Where the heck am I putting this in? I guess in the same place I did before. Connect your oscilloscope to the op-amps output. Op-amps output. What's the op-amps output? Is that going to be pin 4? Well, let's stick it in there to start with, shall we? Let's plug our thing in. No, that's not it then. If I got that the right way around, I do. So what's the output of the op-amp? Ian, what you need is band in the box. Band in the box is going to sort you out. It's got every style in there you could possibly imagine. Already all done for you. Band in a box, mate. Go and look it up. That's your thing. No, I don't want to look at a schematic. I want you to tell me. Right, so this has got 4 op-amps in it, yeah? I've got that going to positive. I mean, I could just plug it in random things until something happens. This looks like it's died. It has, it's crashed. Oh, darn it. Darn it. Is it? Might be some shorting underneath itself. Alright. Okay, that's a little bit better. Alright, there's the thing. So we've got so we got a reflection on that. There we go. So we've got some of those. I mean, I'm just going to have to go with what Moritz says, because they don't really look that much different to me. It's not that way, this way. Right, so buffering and low pass filtering and all that kind of thing. So now we've got a decent triangle wave, so it says. I mean, I don't know, have we? Pin 1, 7, 8 and 14. Yeah, but how are the pins counted? Pin 7. I'm currently in 1, 2, 3, 4. I think I'm currently in pin 5. Does it go down and then back up again? So if I want me to go in pin 7, I can do that. That's there. Oh, look, that looks even better. Let's go with that. So let me spin me what's it again. Pull this back a little bit. That's going worse. That's making no difference. I could be doing this all week. That's definitely worse. So I'll keep going that direction. All extreme corners. Oh, okay, thanks. What way does the initial saw rise? I don't know. Flipping trimmers. Waste half my life playing with trimmers. Oh no, that looks about like me. I mean, that looks alright to me. 1K resistor is on the output. I've got a few of those. So, for that one. Yeah, okay. Cool. So, the original signal looks like that. So it goes up and then down. And then this signal is like that. Cool. I mean, as I say, I'm not really seeing how that's different to the way before. I mean, I'm just taking Moritz's word for the fact that it's now more refined or better because it's been filtered and buffered and all those sorts of things, which is all cool. All cool. So now, there's a problem with our design, is that it only affects the bottom of the output waveform. In a traditional wavefolder, you'll want to fold both the bottom and the top. Okay. To get there, we'll first check out an alternative version which folds just the top of the output. Okay. The only real difference here is the type of transistor we're using. Replace the NPN with the PNP. Since PNP is basically just an NPN, it's Bizarro's twin brother. Everything about it is inverted. Alright, so there's another graph which is showing us it working differently, or invertedly. So in the space between the plus 12 now and the folding threshold, which is minus 450 millivolts, the collective voltage rises as the base drops. Once they meet, they start dropping together. So if we use our triangle wave as an input, we should get an output with a folded top. Right, so now we've got our triangle. We're now going to use that triangle into another circuit in order to make that happen. That's exciting. So to vary the volume of the input, we'll also set up a temporary attenuator using our 10K pot. Ta-da! Okay, great. Once you've set this up, try fiddling with the potentiometer. Right. So back into here, we'll put in our pot. Tricky. Putting our pot in here somewhere. Fitting it in is tricky because our pot's not quite like your pot, so let's bend these up. So that's going in there. For its sins, then we need stupid tiny ones. Why do we need to connect that one over? So simply because some of this is a little bit pedantic. I think a little bit pedantic just to get it all square, but hey. That's good. I'm going to take a blue one, put that across to ground. good. That's that. That's still there. You want me to put a nice big long one from the middle of this over to a P all the way over there. So no longer want this N type. Now I want one of my P types. Slightly weird things they are. And this is going to go on line 35. 3 in, 35 to there. I'm assuming that's 20k and that's staying. This is connecting from the middle of the pot to the middle. Ah, that's not long enough. That's not long enough. It's the middle of pot. This is too long. To middle of this. Oh, that's just stupid. Get in. I have absolutely zero confidence in that being in. Oh, who knows? Was there a middle way, I wonder? Then I've got a leg going over there. There through a 20k, yeah. 20k at the bottom, yeah. Still got that line going over there. I've still got a connection there to make a jump across the bridge. So this connection is from the third one to the middle. Third one to there. I need another brown fella. Jump across. It just jumps across to that 1k there. Damn it. I think that's it. Down there, that goes there, that's there, that goes where, down as well. Once you set this up, try filling and you should see the shape of the output change as the folding effect gets more intense. So we need to put this back. Am I putting this back in the same place? I don't think so, because that ain't doing nothing, because I'm just coming out of the same op amp. So I'm looking at the triangle output. I don't want that. I want the output. I want the output of the folder. So in that case, I need to pop over here, I think. Well, that's interesting. Doesn't really look like it's folding. All I'm getting through there is a through. You should see the shape of the output signal change as the folding effect gets more intense. So I'm using the output of the triangle. That definitely seems to be getting over here from this middle connection, which has come from there, which is essentially the output has gone through that 1k. It's coming into this pot. The pot's gone to ground over there. The middle one's coming over to this. Do I have that the right way up? I do. And that's jumping across there, but this is the other way up and it's inverted, so maybe I'm on the wrong output. Maybe I need to be on the other leg. Let's try the other leg. Ooh, that's different. I have no idea. Well, that's certainly a different waveform to the other one. Got that choice or that choice. See, that doesn't seem to be done anything. It just goes up and down. Whereas over here, you're certainly getting something going on. You could argue that this is being folded into that. Now, if I was to change the level here, it's difficult to see the point at which it folds, really. Any thoughts? You're talking about guitar amps. Those little jumper wires are actually designed for soldering into Vero type prototyping boards. Yeah, well, what do you know? How about that? How about that? Okay, so I don't know. Is that what we're supposed to be getting? Let's just go with it. There is a simulator. Let's just get on, shall we? It's now 9:15, so that's how far we've got to go. Top bottom wavefolder, which adds in another thing there. That might be interesting. And then buffered, so you need a few more op amps jammed in there, I suspect. A virtual ground node. Then there's a more elaborate input stage. Then there's a double wavefolder. I'm thinking that we're probably going to not get all this way. So I think we've done very well. I think we've accomplished something. I think there's a lot more to build out, which is just going to take too long at this point. So let's go back to where we are. I mean, I guess what I'm not getting particularly is when you see wavefolding in a scope. When I do it on other wavefolders, you get a very satisfactory bending and folding over. You know, you see it happen. It's like it ravels itself up and unravels. It's really, really nice, and I'm not really seeing that here at the moment. I'm seeing an alternative between two different, a comparison between two different signals. One where I'm understanding how we're deriving a triangle from a sawtooth, and then I'm seeing that triangle, I think, being folded in half, but I'm not seeing it being folded in half by degree. It either is or it isn't, because it's hitting a threshold. That we're not using anything to adjust that threshold or to see that work. Do you see what I mean? But if everything is working correctly, then I am getting the idea of what's supposed to happen. I don't think I want to spend another 2 hours working to the end of this, because a lot of it is just enhancing and adjusting and getting to the point where you can vary it, of course. Yeah, I mean, of course you can stick a sine wave in to begin with. I could even try to do that. But then I don't know where to put that in, because at the moment it's going into a circuit which is turning it into a triangle wave. So in order to bypass all of that, I don't know what I would do. The point of the sawtooth to triangle conversion is because the VCO within our modular kit, therefore the only one you would have if this is your modular that you're building, is going to be sawtooth or square, and so that's why we're doing this conversion into a triangle. So it all makes sense. So bypassing that with something else is, like I say, I don't know how to do that, and that defeats the object of building the DIY thing. Do you see what I mean? See what I mean, man? Speed in the scope? What about the speed in the scope? Yeah, Ken, I agree. I think the top and bottom would do. Let's go with that and see what happens. Excuse me, because I'm still a little bit under the weather. So top and bottom wavefolder. So the question is, apparently, how do we combine these folding circuits into one? Apparently it's easy. All we've got to do is wire them together. That's what we like. Then if we send in our triangle wave on the left, we can pick up the top and bottom folded output on the right. So, okay, yeah, you can tell they're different because of the pointy bit is going slightly differently. Oh, look, there's a little bridge. It goes under the bridge. That's nice. So you send them in, it goes to both, and you combine the outputs. Brilliant. Oh, excuse me. So at 0 volts base voltage without a connection, the thing would be at plus 700 millivolts, while the other one would be at minus. Okay. Wire them together and we get 0. Yeah. Now we increase the base voltage. One opens up, one closes down. That's all good. This forces us to pull more current from the positive rail through 20k, which in turn causes the voltage at the collectors to drop. At least until we run into the folding threshold. Same idea in reverse. So this way we get two folding thresholds, one slightly above and one slightly below the 0 volt line. That all seems fair enough to me, you know. So here we go, a little bit more complexity, and let's see where this gets to us. So it says, unfortunately, we can't just attach an output socket to the transistor's collectors because that would mess with the core mechanism by pulling more current through it. So they're going to have to stick a buffer on the outside of that. See, I do understand the reason for these things. You know, a buffer is kind of a way of transferring voltage from one place to another so that you can do more things with it and the original one doesn't get affected by it. So, yeah, right. So, right. Let's unplug that for the minute. So what's changed? Not a whole lot. All we got to do, apparently, is stick... well, that's no longer going... Oh, yeah, it's try to... Oh, okay. There is a little bit of something going on. That's staying, apparently. Let me just unplug the positives for a minute. I'm going to take this cable out because it's bothering me. I want one that's... See, is blue not quite long enough? Oh, maybe I found another one that will work. So yeah, let's get this top and bottom done, and then I think we can call it a night. So that can stay there with that line going to there. It has bumped it up a little bit, so let's do that. So this is going up to 40, is that right? Yeah. This is coming up with it. And so is this fella. Is that last leg? Yeah. It's that last leg. Meanwhile, another one of these is going to go in this way around. And it goes that same leg, and that ends up on that one there. Brilliant, nice, like it. And this is going from the middle to middle. It still doesn't quite work. Well, I'm just going to have to bend the thing. I don't have a perfectly... let's just try that a little bit harder. Let's do that. Middle to middle. So, middle. middle. Okay. I need a little wire. Gonna go ties the two middles together. Yeah. Middle to middle. I think that's all, the only adjustment required. Those two legs, do they go anywhere? Only to each other. That goes that 20k. Okay, good. So where's the output in all of this, I wonder? Is it still over here? No, there doesn't seem to be anything. Is it over here? No. Over here. Oh, okay. I've broken it. So, if you check again on the voltage at the two transistors collectors, you should see the top and bottom of the input get folded over. So, if I go over here, okay, there's my triangle. This is plugged in. That's middle, going to middle on that one. That one's that way and that way up. Plugged my power back in. That's that way up. Does it do it where they both are? Ooh! Ah! Look at that. That looks pretty folded, doesn't it? Yeah, that's more like the sort of thing I'm kind of looking to get when I talk about folded. Yeah? That's very interesting. So there's my sawtooth. Then gets turned into a triangle, which then gets folded. Yes, there's a folding going on. Love it, love it. So we'll simply route the voltage through a non-inverting op-amp buffer connected to the output socket, right, and that will work. There's an alternative approach will help us streamline the design a little bit. Okay, so then we do some buffering to buffer the wavefolder, bloody blah blah, bloody blah, bloody blah. We just did this a minute ago, and I mean we could. Does this mean we would actually hear it? All right, so because that was easy and that's only just 2 hours, heck, let's do this last bit and then we'll actually be able to hear something, and that would be awesome, I think, an awesome place to finish. Right. So, do we need to understand that? Not really. We just know that we're going to create a buffer which is going to use another op-amp and a couple of transistors. Or not really. It's just going to use... Yeah, it's going to use a section of the op-amp at this end and give us our output. That's worth doing, I think. Something to do with a virtual ground node. Behaves just like a path to ground without actually being one. So connecting the collectors to the op-amp's inverting input through a 10K is functionally the same as connecting them straight to the ground. Why not just put them straight to the ground? With this change, you can finally listen to the output. Let's do it. Yeah, let's do it. Right. So not a whole lot going on. What diagram? Was there a diagram? Whatever. Right, so let's go. So we're going to take a brown one. There seems to be something crossing the streams here. That's great. That takes another 1K. 1K. Takes that way out somewhere else completely. So that 1K from there goes nuts. Over there. Good, that 20K is still in play. That's the same. There's another thing going on there, which goes to that first pin. And then that. Ooh, oh, rats. Yeah. So that's coming into our transistor. Got two 10Ks to squeeze in there somewhere. That's the same. I've got a little connector to go in there. That's between the outside and that first pin. 10K, 10K, 1K, 10Ks, two 10Ks. Yeah. So one goes between those two top pins. Another one goes to the same pin 2 and that one pin there. Pin 2, did I say? I did. That pin to there. Still got that. I need to bring this 1K over. Need to put in another socket. Like so. And go to ground. Awesome. Right, let's see if I can get some sound out of my thing. No, because I know what I did. I plugged in the Mini Freak. So sorry for the noise. just trying to find a channel I can plug it into. Let's plug it into there. Let's see if I can get an output to start with. Sorry, hang on to your ears. Okay, good. So that's working. Probably got far too much reverb on everything. Right. So that needs to go in there. I don't know if that's impressive or not. Let's plug this in to here. We seem to have lost a lot. Ah, that'll be because I haven't plugged the power back in. Oh, bloody hell, plugging it in the wrong plit. Okay, now we've got something going on. What is that about? Why is it all wobbly? I mean, over there. That's the signal coming in. Well, I don't know. So, check this scope. You'll see how it crosses the folding thresholds a second time at maximum volume but doesn't get folded. It's because we're going deeper and deeper into saturation in the same transistor. Alright, well, I don't quite know exactly anything at all. But look, we're getting a strange waveform. And that definitely changes as I increase the level. But it may well be I've done something bad in here. No, I don't know that I have. Oh no, there's definitely a line there I've missed. Hang on. I did not ground pin 3 on the op amp. Pin 3. Need to go to ground. Oh, that's better. Possibly. Oh, I don't know, I quite liked it how it was. So there's definitely some folding going on there. But that's all I'm getting. So I'm first of all getting my folding from sawtooth to triangle. That's the first bit that's going on. And I'm definitely getting that bottom half folding over. I'm not getting the top. So it says, you'll see how it crosses the folding thresholds a second time at maximum volume, but doesn't get folded. That's because we're just going deeper and deeper into saturation in the same transistor. I don't really see this crossing folding thresholds. Is that what they mean? Is that's when it does that fold? I suppose. Are the two transistors the right one? Yeah. I like that. I definitely like that change. That's very satisfying. I do feel that other one should be doing more. I do have that right, don't I? That's the right way up. That's the right way up. Two different ones. I think I am seeing what Moritz is saying. What would just be really awesome would be to see that top waveform fold. That would be great. I'm just not quite seeing that. Definitely seeing the bottom one go, just not the top one. And I'm not entirely sure why. I might have got something a little bit wrong in here. I'm not entirely sure. Interesting. So I think that's probably far enough. So after that we get into an input stage in improving the input, which is fair enough. And it talks about setting the input volume so it's just shy of crossing the thresholds. All right. Okay. All right. And then a double wavefolder. He's saying that it's a bit too tame. It is a little tame. Yeah, I can see that. But, you know, we're just trying to understand the idea. Because that is what we're getting, isn't it? That's definitely what we're getting. So then he goes to a double wavefolder and then a 2.5 times wavefolder. Wow, that's crazy, man. Just getting out there. And then that's a lot more to do, which I don't think we'll do now. I think we've done enough. So what we will do then is we will look forward to the soldering. So I think we got to some bottom of that. To some, oh, bipolar junction. Was that what the BJT was about? Cool, right. Good, good, good. So the build guide. The actual circuit. It looks like a relatively easy soldering job because it's quite a small board. Not a whole lot going on with that. Okay, good, good. So I think we'll probably leave it there. That was quite interesting. I mean, I'm still very interested in this, you know, in this waveform and what we were able to get out of it. The folding that we saw, I understand. Do I understand anything? What could I grasp through it? Something about a saturated transistor. That at some point, when you're trying to pull current through a transistor, and at some point there isn't enough, and so the voltage has to start going up. And that results in an inversion. So you've kind of got a graph line that's going up, and then it inverts as it's trying to adjust the voltage to give you more current. Something like that. Something like that. And using two different transistors, which are essentially opposites of each other, means you can fold the top and fold the bottom. What was very successful was changing the sawtooth into a triangle. That worked really well. The other bit, yeah, as I say, a bit tame, but they're going to do more wavefolding in it. So when we actually have the wavefolder finished, we should have a lot more wavefolding action on our little thing here. Yeah. So we are going to do this next Wednesday, not tomorrow. I've got other things, unfortunately, I have to do tomorrow. I'm trying to squeeze all this in to things. But next week is half term, but I've managed to square away next Wednesday evening for the same as we did tonight. But what we'll do is we'll do the soldering. All I've got to do now is make sure that this kit doesn't end up all over the place somewhere, so then I can't find the parts. But hopefully it should be fine. It should be fine. I think so. So that's the plan. That'll be a plan for next Wednesday. Obviously I'll post a link to the stream once I've got all that together and confirmed it. Shouldn't be a problem. Alex in the chat is recommending going and watching some more of Moritz's videos. Always a good idea. Always a thoroughly good idea. My intention is to just throw myself at this and try to bumble my way through it to replicate the user experience of someone who doesn't really know what to do. That's what I'm trying to replicate here, and I think I do that quite well. There is a ton more information to get. Moritz's video, Moritz Klein, his video channel, goes through all of this. It goes through every concept. It takes you through all of the parts that have been put together and all of the circuitry behind all of this. And that a lot of that ends up in the build guide for this, which is the thing I've been trying to express through these series of videos. But there's tons more you can learn. There's loads within each manual as well, including appendices and bits and pieces like that. In my the strangeness of my brain tells me that the reason I'm trying to do it this way is, one, partly because I don't have the time to look into it incredibly deeply and have all that information beforehand, but also because I'm trying to resist that situation where it's an expert explaining something to you. As soon as you have an expert explaining something to you, while that's great and good for a teaching opportunity, it doesn't ever come from your standpoint, doesn't ever come at the same place, and lots of assumptions are being made. It's like a bit like the chat that I get some wonderful experts within the chat throwing me bits of information which are useful but require such a background of things that they don't make a whole lot of sense to someone who's coming to it afresh. So I'm trying to bring a fresh perspective to it, which ends up a bit hackneyed and fudgy, but that's how things are sometimes. We'll do, once this is all finished, so at the next one, once we've finished it, we'll just get together, we'll kick back and we'll try to make some tunes with the with the modular, and we can talk about the whole experience at that point, to sort of feedback on the whole 10-11 months it's taken us to build this thing. I think that would be fun, and yeah, we can talk about it more at length at that point. That'll be good. Next Monday's good for you, is it, Ken? Great. So there we have it. I hope that's been useful. I'll see you next week, all being well, but I will post links to it because there's all sorts of things could happen between here and then, so I can't absolutely guarantee that that'll be there. But I'm keen, very keen to get this soldered and in there and feel like the whole thing is complete. That would be awesome. That'd be very, very satisfying. So good. Thanks very much for sticking around and being with me this evening. I hope that's been fun. I appreciate your time, and I'll try to find the right button to play my outro, and I'll see you next time. And makes tunes and that.